Hi sir, this is Nitin from CSC branch. The allotted topic for CA2 assignment was about Boolean algebra. At the end of the session, we know about the introduction to Boolean algebra, basic Boolean operations of and, or, and not, Boolean algebra laws and theorems, Boolean expression and truth table, simplifying Boolean expression, corner maps and minimization techniques, digital logic gates and circuits, Boolean algebra applications in computer science, Boolean algebra and digital design. At the end, conclusion and key takeaways. First, the introduction to Boolean algebra. Boolean algebra is a fundamental mathematical system that underpins the digital electronic devices. It provides a powerful framework for representing and manipulating logical statements and operations. Basic Boolean operations of and, or, and not. And the AND operation returns true if both inputs are true and false otherwise. It represents the logic conjunction of two or more propositions. Or the OR operation returns true if at least one of the input is true and false only if all inputs are false. It represents the logical disjunction of two or more propositions. And the next, the NOT. The NOT operation negates a single input, returning true if the input is false and false if the input is true. It represents the logical negation of proposition. Truth table. The basic Boolean operations can be represented by using truth tables, which systematically enumerates all possible input combinations and their corresponding output. Boolean algebra laws and theorems. The commutative law. The commutative law states that the order of operands in and or operations does not affect the result. This allows for more flexibility in simplifying complex Boolean expressions. Then is the distributive law. The distributive law allows and or operations to be combined, enabling the simplification of complex Boolean expressions into more efficient forms. Identity law. The identity law states that there are specific values for and or operations that will always result in the same output regardless of the other operand. It provides fundamental Boolean algebra movement. This provides a foundation for Boolean algebra and manipulation. The next, the Boolean expression and truth table. The pyramid shows about the Boolean expression, truth table, and evaluating expressions. Logical statements using Boolean variables and operations. Truth table, the tabular representation of all possible inputs and outputs. Evaluating expression determining the outcomes of a Boolean expression. Evaluating expression determining the outcomes of a Boolean expression. Boolean algebra is the foundation for digital logic design. Boolean expressions are composed of variables and logical operators like and, or, and not. Truth table systematically lists all possible input combinations and corresponding outputs, providing a comprehensive way to analyze and verify the behavior of Boolean expressions. Simplifying Boolean expressions. Identity redundancies. Examine the Boolean expression and identify any variables or terms that can be removed without changing the overall logic. Applying Boolean algebra laws. Use the commutative, associative, and distributive law to rearrange and simplify the expression. Minimize using corner maps. Construct a corner map to visualize the expression and find the most compact minimized form. Minimization techniques. Corner maps are a powerful graphical tool for simplifying Boolean expression by visualizing the truth table as a grid. You can quickly identify patterns and apply minimization techniques to reduce the number of logic gates required. Minimization techniques is like grouping and pair finding allows you to derive the most efficient Boolean expression, optimizing for cost, complexity, and performance in digital circuit design. Digital logic gates and circuits. Boolean algebra is the foundation for digital logic gates and circuits. These gates, such as and, or, and not, are the building blocks of digital electronics and computer systems. By combining these basic gates, more complex logic circuits can be designed to perform a wide variety of digital functions. Boolean algebra applications in computer science. Digital logic designs. Boolean algebra is a foundation for designing digital logic circuits, including logic gates, combination logic, and sequential logic, which are building block of modern computers and digital devices. Second, the programming and algorithm development. Boolean expression and operations are essential in programming languages for conditional statements, logical operations, and algorithm optimization, enabling efficient and powerful software solutions. The third, computer architecture. The principles of Boolean algebra are applied in the design and implementation of computer processors, memory systems, and other hardware components, ensuring reliable and high performance digital system. The fourth, the cryptography and cyber security. Boolean algebra is used in cryptography algorithm and secure communication protocols, helping to protect sensitive data and system for unauthorized access and threats. Boolean algebra and digital design. Digital circuits. Boolean algebra is the foundation for designing digital circuits and electronic systems. It provides the mathematical framework for representing and manipulating digital signals and logic gates. Integrated circuit. By applying Boolean algebra principle, engineers can optimize the design of integrated circuits, microprocessors, and other digital components that power modern electronic and computing devices. The third, the digital design. The Boolean algebra enables digital designers to express, analyze, and simplify complex logical functions, leading to more efficient and compact digital systems and architectures. At the end, the conclusion. It is the representation. We have explored the fundamental concepts of Boolean algebra, its operations, laws, and applications in computer science and digital design. Let's recap the key takeaways and consider how this knowledge can be applied in real-world scenario. Thank you, sir.